Okay, welcome. So today is a very special lecture because we have Steve Yablo. So I thought it would be cool to have Steve here for two reasons. The first is that he invented Yablo's paradox. I thought that would be pretty cool. And secondly, because he is perhaps the world's expert on omega sequence related paradoxes. So, I thought you could hear all about them from the man himself. So welcome. Yeah.
It might be worth mentioning that Augustine and I are probably the people in the world who care the most about backward omega. So there isn't a lot of competition for this position. So I'm Steve. I'm going to try to organize this class around the distinction that Quine draws that's very useful. So about, in general, there's these weird situations where you have some plausible looking premises and they seem to imply something unbelievable by a valid looking line of argument. Quine draws a three-way distinction. He says, first of all, there's paradoxes versus antinomies. So let me start with paradoxes. Paradoxes come in two kinds. A veridical paradox is a paradox where the argument is actually considered to be acceptable and you wind up just believing the crazy seeming conclusion. In other words, the paradox was just an argument for a very surprising result. So an example of this might be if have you guys done Russell's paradox or no? Yeah. So Cantor's got this amazing argument that says, however big a set you form, you can get an even bigger set. That can sound sort of crazy because the first set could have been completely infinite. It could have had as many things in it as you might have wanted. But people by and large accept that Cantor is right, that there's just like no biggest set cardinality-wise. You can always sort of get a set that's has many more things than the one you started with. Incidentally, if you ever do Russell's paradox, which I don't know if you, it might be worth mentioning that I believe that Russell came up with that paradox while trying to show what was wrong with Cantor's theorem. Anyway, so that's a veridical paradox. It seemed like you couldn't believe this horrible conclusion, but as time passes, one generation dies off, another one comes along, people say, that conclusion was actually right. You last generation people were just like too rigid. You just weren't imaginative enough. So that's a veridical paradox. A falsidical paradox is sort of what you'd expect to happen, which is you find some mistake in the argument. There's some false move. Now, the interesting thing, so in both of these cases, the veridical and falsidical paradox, you find a culprit, right? There's some particular thing that has a different truth value than you thought. The really bad case, this is what Quine calls an antinomy, is where you can't accept the conclusion and you can't find a mistake in the argument. And Quine's picture of sort of the evolution of paradox studies is you have these antinomies where it's genuinely unbearable situation. You can't give up, you can't reject the argument, you can't accept the conclusion. And over the course of time, even if it seems impossible early on, the antinomy should become a paradox of one kind or the other. Either you find a new sort of mistake you hadn't been aware of, or you develop a new tolerance for this crazy seeming conclusion. So the way I want to organize this is I want to look at some paradoxes under the aspect of what kind of paradox are they, veridical or falsidical. And I'm going to try to identify principles that you might have seen, that might have seemed to you absolutely unquestionable, but the examples seem to show that they're at least not obviously right. And some of these you might already have heard of, and Let's start with Zeno's paradoxes. They're paradoxes of infinity. You've probably, did you talk about Zeno's paradox? Yeah. So usually they're paradoxes of a certain kind of infinity, a mega-type infinity. A mega-type infinity is you've got a first thing, second thing, third thing, fourth thing, fifth thing, etc. ad infinitum. There's another thing, which you've already heard of, which is sort of backwards a mega-type infinity, which is where you have a ... n plus first thing, nth thing, n minus one thing, etc. So most of the paradoxes to do with infinity that philosophers have talked about are omega-type paradoxes. So you've got like, I can't get from this end of the room to that end of the room. Why not? Because I'd have to get halfway there first, and then I'd have to get half the remainder of the way and half the remainder of the way. And this is like infinitely many tasks. And how am I supposed to complete infinitely many tasks in finite time? So this is an example of what to us nowadays is just a clear, I guess, veridical, I guess it's a falsidical paradox, because you're assuming what I just said, you can't complete infinitely many tasks in finite time, is just no longer accepted. You can if you speed up fast enough. If the m plus first task takes half the time of the nth task, you can do it. So that's why I have on the handout, it says infinitely many things can't happen one after another in finite time. That's just wrong. One thing can happen after half a second, other one quarter of a second later, other one eighth of a second later, et cetera, et cetera. Then you get infinitely many things happening by the 1 second mark. OK. Now that was an omega paradox. One of Zeno's paradoxes, which is very similar, the dichotomy paradox, is a backwards omega paradox. The way it goes is instead of letting me go halfway across the room and then finding a problem with my sort of completing my path all the way to the back of the room, it tries to create a problem right at the beginning. It says, well, look, before you can go halfway across the room, you have to go a quarter of the way across. Before you can go a quarter of the way across, you have to go an eighth of the way across, et cetera. So whenever you set your sight on some goal, some sort of intermediate goal that would have to be completed before you can make it to the other side of the room, it turns out you can't even get there because there's another thing you had to have done first. So that's got the backward omega structure because the tasks that I can't complete are ... going a 16th of the way across, an eighth of the way across, a fourth of the way across, a half the way across. So that's backward. It's got ... at the beginning. That's the key to a backward omega structure. Here's one other interesting paradox that sort of combines the forward and backward omega structures. This has to do with basically Newtonian mechanics and how do we understand Newtonian mechanics and what are the rules. So we're used to thinking, and they teach in physics classes, that there's these basic laws like conservation of momentum that are sort of characteristic of Newtonian processes. But imagine the following. We have an infinite string of balls ranged between, say, the 0 mark, let's see, for you, the 0 mark and the 1 meter mark. Okay. The first one's at the 0 mark. The second one's at the half meter mark, 3/4, et cetera. They get smaller and smaller fast enough that this all fits in. Okay? So maybe the nth ball is 1/4 to the n in diameter. But they get denser and denser. So they all weigh the exact same amount. So if I start the first ball going 1 meters per second, it hits the second ball. The second ball has the same mass as the first, so the velocity should stay the same by conservation of momentum. And so the second ball will hit the third and the fourth and so on. But the velocity will constantly be 1 meter per second. Okay, so at the end of a second, all the balls will have given up their momentum to the ball immediately after them. But if that's the case, if every single ball has given up its momentum to the ball immediately after it, then what's going to be happening? Is any of the balls going to be moving? That's my question to you. Is any of the balls going to be moving at this point? Trick strategy. If a ball was moving, it would be ball number n for some value of n. Okay. So now you tell me what comes next. Can ball number n be moving at the end of this process?
If the ball n were moving, it should be ball number n plus 1 that's moving. And you can always, yeah.
We already know that n stopped when it hit ball n plus 1, because that was it imparted all of its momentum to the next ball. Yeah. So that one's not moving, and you can make the same argument for any particular ball. None of them are moving at the end, at the 1 second mark. So that's an omega type situation, which is interesting because it seems to show that momentum isn't conserved in this kind of scenario. But now I want to make it a backward omega scenario. The way you do that is you note that Newton's laws of motion are time reversal invariant. Any lawful process going in one direction is lawful going in the other direction. So instead of thinking at the 1 second mark all the balls have stopped, Let's run it in reverse. At the 0-second mark, none of the balls have begun to move. Every moment after the 0-second mark, some of the balls are going to be moving. Okay? At the 1-second mark, well, let's not worry about it. I guess I didn't really say what the, I guess at the 1-second mark, the ball will kind of hit my hand, which was the one that was, in the original way of doing it, was pushing the balls along. But the key thing is, the balls are just sitting there doing nothing. And then all of a sudden, they start kind of gathering speed and moving along. It's a completely indeterministic sort of scenario. But it seems like it's compatible with Newton's law. So that's an example of Newtonian indeterminism. Okay. I actually do not know what people say about that. I mean, I'm kind of curious. But let's move on a little bit, because I've got some other examples of indeterminism that I want to mention that are more of a logical nature. So you've heard about Benedetti's paradox of the gods, right? Is that right? They did that, yeah. Should I do it again?
Yeah, we didn't talk about gods, but we talked about the bear.
Oh.
Yeah, there was a bullet.
He's a heathen, kind of.
Yeah.
He does, it's essentially gods. It doesn't really work unless it's gods. So here's how it goes. So you're trying to travel from the 0 position, say, to the 1-mile position along a certain road. And not only is God against this plan of yours, there's infinitely many gods that are all against this plan of yours. And they make this incredibly devious system of backup plans to make sure that you don't reach the 1-mile mark. And here's how it goes. God 1's job is, if you even make it as far as the half-mile mark, God 1 will put down a wall to stop you, so you can't get past that. God 2's job is, if you even make it as far as the 1/4-mile mark, God 2 will put down a wall to stop you, etc., etc. Now you'd think, with infinitely many gods bent on sort of interfering with your plans, that you were not going to be able to get very far out of the starting gate. But again, if a god stopped you, it's God n for some value of n, right? But if you think about it, God n really wasn't in a position to stop you, because you should already have been stopped by God n plus 1, right? So I'm not sure this argument quite goes through, but there's something a little bit, you could try to argue as follows. If the gods behave the way they're supposed to, none of them can actually touch you, because everyone is, so to speak, arriving on the scene too late. You already should have been stopped. Okay, so you actually make your way all the way through. Yeah?
I understand the paradox, but it says on this sheet that this could bring out a Hegelian contradiction. But what is that? I'm not familiar with the term.
Yeah, I barely am myself. So we have a responsible kind of mature attitude towards contradiction and paradox. We think if you find a contradiction, something's gone wrong, you better go back and try to fix up your system. There are other people out there who revel in contradiction and think that the world is itself contradictory in certain ways. So you get this idea in some versions of Marxism. You get this idea in the philosopher Hegel, who I'm referring to here. Hegel thought that, and it's an idea that goes back to the ancient Greeks, that the very notion of moving from point A to B is contradictory. There's something contradictory about it. One way to see what's contradictory about it is, look, you can break that whole time period up into momentary moments of time. There's no motion happening at moments of time, but the whole period is just made up of moments of time, so there's no motion at all. Okay? That would be one kind of argument. We don't find that very convincing. But the thought is going to be this. Somebody who already wants to think that the world is like contradictory, because I mean, it would be really cool if it was, right? This gives them a tool they could use to argue for that. They can say, look, Hegel, never mind who Hegel is, 19th century philosopher, thought various things were impossible that aren't. He says, look, Hegel was right because of this paradox, because it seems like it has to do with motion, seems like it's causing trouble. Yeah.
So just a quick parenthesis. One thing I want to point out is that I spent last weekend in New York, And the reason I was there is I wanted to interview a contemporary Hegelian. So I interviewed someone who thinks that contradictions could be true. And in fact, he thinks that there are some true contradictions. So there are some sentences of the form P and not P, which are strictly and literally true. So I'm going to edit the interview and put it on the website in case you guys want to see it.
Is this GP?
GP, Graham Priest.
Well, actually, what I'm about to say next is from an article I wrote in. So Graham Priest is the guy I was thinking of, actually. He said, this shows there's really a problem with motion. And so you've heard of Yablo's paradox, and then I heard of this Bernardetti's paradox. And it occurred to me that you actually could embed the one in the other while at the same time wiping out all vestiges of motion from the paradox of the gods. And it goes like this. So you get rid of the guy who's trying to move from from 0 to 1. The gods are just doing a totally kind of self-sustaining sort of game. They're not trying to block anybody. They just set themselves the following rules. They say, look, we're going to call off yes and no in reverse order. So God m plus 1 I'll call, then God n, then God m minus 1, and so on. And the way it's going to work is this. And you'll recognize perhaps the similarity with Yablo's paradox. The rule is this. If all the gods before you have called no, then you call yes. Otherwise, you call no. Okay. If you think about it, there's no problem with any particular god doing what they're supposed to. You just look ahead. They all called no. I'll call yes. There's not a problem with particular gods doing this. It's not a locally impossible thing to do, but it's a globally impossible thing to do. Why? Because if I'm God n and I'm getting ready to call yes, that means all the gods, the higher numbered gods, have already called no. But then God n plus 1 also has the property that all the gods calling before her said no. And so she should have said yes already. So another way to put it is, by the time I get around to carrying out the job that's been entrusted to me, it's too late. The job already should have been done. And if you just sort of work it through in the same way as with the other paradox, you'll see that there's no way for the gods to stick to this enormous plan. Here's another example with the same sort of quality to it. So here's something that any god can do. If you get a natural number, pick a bigger natural number. That's no problem for a god. Natural numbers are finite. You just got to add 1. Imagine the gods make this kind of plan in advance. They say, look, again, we're going to call off in reverse order. And we're just going to do what I just said. Each god will call a bigger number than the god before. Okay? What's going to happen in that scenario? Okay? So God n plus 1 is supposed to call a bigger number than, so God 1 is supposed to have a bigger number than God 2, bigger than God 3, bigger than God 4. They're going in reverse order. So think about it for a sec. Give yourself 30 seconds and say, what's going to happen as the gods attempt to have this increasing sequence of numbers starting with ... So let me just give you a hypothesis, because something like this is going to have to be true if the gods can carry out the plan. Let's say God 1, I'm going to have to say some numbers. Let's say God 1 says a quadrillion. Okay? Now, fill in the picture. What did the previous calling god say? So God 1 says quadrillion. So what did God 2 say? I know we weren't there, but what could God 2 have said?
Quadrillion minus 1.
Okay. Then what did God 3 say?
Quadrillion minus 2.
Okay. And what did God quadrillion say?
0. Or, I mean, I'm not by 1 error, but...
Yeah. 0. So then what did God quadrillion plus 1 say? Well, there's no natural number smaller than 0, so they would have had to say 0 too. But then God quadrillion didn't follow the plan. Okay? So there's just this huge bottleneck that happens sort of holistically through the whole sequence of gods that particular gods don't run into, because again, it seems like there isn't a problem, because when it's any particular god's turn to act, the problem has already happened. So that god can say, well, it wasn't my fault. Every god can say it wasn't my fault. It's none of their faults. But it's like a case of collective responsibility, as they say. It's all their faults together, even though every single one of them does what they're supposed to do. So that's a case where it seems as though something should be possible for all the gods to do, but in fact, it's impossible. Here's a case where you might think the outcome was necessary, but it turns out not to be. So suppose we got all these gods lined up, and they all just love the number 1. And so they all say to themselves, let's just have a big fat string of 1s, okay, all the way from God Kergillion to Kergillion minus 1, ... 3, 2, 1. And they make the following observation. They say, well, look, since this is obviously easy, we could all call 1. I mean, that's not really that hard for a god to say 1, okay? But they say, look, since we're all saying 1, we could equally well follow this rule, which is just copy what the previous god said. They'll have said 1, so I'll say 1 as well, right? If they can do it right, then they'll already have done it when it gets to god n, and so god n will be just doing this. To call 1 is the same thing as calling what the previous god said, okay? But now this is other bunch of gods, the 0 gods. They have a very similar idea, except they love the number 0. They want to all call 0. Now, certainly, when they get together for their pre-game sort of meeting, they say, well, can we do it? Say, you bet we can do it. Look, I'll show you right now, 0. Each one tries their vocal cords. They call 0. It always works. They say, well, since we're all going to be calling 0, it would be just the same if we would each follow the rule, call what the previous guy said, because it's going to be all 0s up to your point. Okay. So you've got these two groups. This group of gods is all calling 1. This group of gods is all calling 0. What are the rules they're following? This group is following the rule, say what the previous guy said. This group is following the rule, say what the previous guy said. That's the same rule. It's the very same rule. Okay? So it seems like determinism, so to speak, as far as what each god does, given what the previous calling god did, is compatible with indeterminism for the whole sequence. It's like the Newtonian sort of situation. The gods could all tell themselves, I'm just going to call what the previous one did, and there's 2 possible outcomes. They could all call 0 or all call 1. Okay? So that's okay. So no particular god will have any feeling of having any choice in the matter. The die will already have been cast by the time it gets to them. Nevertheless, there were 2 possible outcomes. So it seems like the outcome should be determined, because what else could influence the outcome but what particular gods are doing? And it's determined what particular gods are supposed to do. Just repeat the previous thing. But although that's determined, the total outcome is not determined. Now we're going to get to something genuinely. So this is the kind of stuff where people say, oh yeah, this might make you nervous the first time you hear about it, but you can get used to it. This is all cool. Now we're going to get into some territory that makes me tremble a little bit. We're almost there with the paradox that I think Augustine did with you, the hat paradox. Have you done the hat paradox? Could someone just tell me the hat paradox?
So the basic idea in the hat paradox is that you have infinitely many individuals lined up. They're all wearing a hat of either red or blue, and that So they're all wearing a black or white hat, and the idea is that you're trying to. So if someone calls out correctly their own hat color, then they live. If not, they die. And so you're trying to see how many people you can get to live or die with this infinite string of things. You can't see your own hat color, so the sort of obvious answer is you have a 50-50. But the really not obvious answer is you group everybody into these sort of boxes of possibilities that only differ by finite sequences, and then somehow you can make sure only a finite number of people die.
Right. Right on. How can you make sure? What's the deal you make in the pregame meeting to ensure that only a finite number of people die? I mean, the real paradox is just there is a deal that you can make, but what is the deal, just out of curiosity? Yeah.
The last person counts how many people are wearing either the white or black hats, and decides like that this person will either say the even number or the odd number, because there's so it'll be the even or the odd, and then with that, so that person has a 50-50 chance of surviving, but and if they don't, then the person in front will be able to count, like if the person behind said odd and now there's an even number, if the person behind said like white and now there's an even number of white hats in front of me, but that means that I have a black hat or whatever, however it would work out.
So you found a way for almost everybody to live, only like a maximum of one person died.
Assuming a finite number of people.
Right, a finite number of people. But let's say we're back in the God situation. So there's infinite number of people, okay, and they're calling off in reverse order. Although the calling off in the order you mentioned also could work as well. But let's stick to the old plan. They're calling off in reverse order. There's a plan that there's infinitely many of them. There's a plan that they could make that has the result that at most finitely many of them die. Yeah.
You group every possible sequence that exists into several separate groups. In each group, you place any sequences that differ only finitely. And then from each group of sequences, everybody agrees on in the pregame meeting one specific sequence that they're going to assume is the representative sequence if such a sequence shows up in the real situation. If they all respond either white or black based on that representative sequence from that group, then it's guaranteed that only finitely many of them will die.
Because they'll be guessing a representative from that group, and everything in that group is only finitely far apart from everything else. Yeah, so only finitely many will be wrong. Right. And I personally find that mind-blowing in that it's sort of, if they all hit on the same sequence, then everything goes okay, but if they like pick different sequences, then it wouldn't, I mean, it just sort of seems bizarre to me that they're all agreeing on a sequence should have this result. I am prepared to believe that this is one of the, of course, the argument for how this could work involves picking a representative sample from this equivalence class or this orbit, and that involves a pretty heavy-duty application of the axiom of choice. But we're used to thinking, and I gather you had a full proof of the Banach-Tarski paradox, that from the axiom of choice, much craziness comes, but we're just supposed to like accommodate ourselves to that craziness because it's just, that's what it is to grow up, So this is supposed to be just one of those crazy consequences of the axiom of choice that people can arrange, that even though they have no information about their hat, that almost all of them will be able to guess correctly. And to use the trick that you mentioned, if they could, even if there were infinitely many of them, we already know by the first trick that there's only finitely many mistakes, so to speak, finitely many differences between the equivalence class that we see and the chosen representative. And so it's as though the first person was looking at finitely many people, because they just have to look to the last departure, so to speak. And then they can do your trick. And then almost everybody, only one person could be at risk, even with infinitely many hats. Now that's really bizarre. So people know nothing about a certain matter, and all but one of them get it right. Maybe that's a bit of an exaggeration, but yeah. Okay, so during my months of thinking, this is impossible, I can't believe this, and having people like Augustine try to talk me out of it, say, don't you know that, the probability isn't really a half, it's unmeasurable, and da da da. That is not an imitation of Augustine's voice, as you know. But yeah, but people, but I was just looking around for some evidence that this couldn't really work as planned. The only kind of hole in it that I could see is it's assumed that if everyone gets together in the pre-game meeting and decide they're going to do a certain thing, they're going to do it. We've already seen that might not be quite right with the case of like saying what the previous god said, when you wanted all whites or you wanted all blacks or all ones or all zeros. The question is really one of collective power. If infinitely many agents get together and say, we're all going to do the following, can they do it? It seems obvious that they should be able to. Well, not in every case, because there are some cases where it's impossible for them all to do it, like the Y variant of the Benedetti's paradox, where they're calling off ones and zeros in reverse order, or the one where each god calls a larger natural number than the one before. But if it's possible for them all to follow the rule, and they want to all follow the rule, it would seem that they will all follow the rule. You know, there's many a slip, twixt cup and lip and all that, but nevertheless, if our main goal in life is to follow a rule, and it's possible for us to follow the rule, then doggone it, it seems like we ought to be able to follow the rule. So let me give you one example to sort of cast a bit of doubt on that, at least that puzzles me a little bit. This is when it comes right at the end, actually, just mention it. Like, sometimes it might not be obvious what, even if it's possible to follow the rule, it might not be obvious what the solution is, what everyone has to do to follow the rule. So here's a rule. God n is supposed to look at the gods ahead of them. They don't look all the way down the line. They just look at the two previous calling gods. Those two previous calling gods either agreed or disagreed. They both said 1 or 0, that's agreeing. Or one of them said 1, the other one 0. That's disagreeing. Here's the rule. Say 1 if the previous two gods disagreed. Okay? Now, it is possible for them all to follow that rule. There's a couple of ways they could do it, but here's one. 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1. Okay, that's a solution to that kind of constraint. Now, I haven't told you that the gods know that that's the solution. So if I say, look, here's a rule they could all follow, they all want to follow it, are they going to follow it? It's not at all obvious. Maybe they don't even know how. They don't know what the solution is, so to speak. They can all do their part, but it might already be too late for them to pull it out because the mistake might already have happened. Here's another example. Say 1 if the limiting density of previous calls, as you sort of increase the window going back from yourself, is well defined. So I convinced myself at some point, the only solution to that is 1, 1, 1, 1, 1. But if you tell a bunch of gods, say 1 if the limiting sequence, the limiting sort of density, so to speak, is well defined of ones in the earlier calls, how are they going to know to all say 1? They'd at least have to do the math, right? There's no guarantee they'll do the math right. Even if they did do the math right, again, by the time it's anyone's turn to call, it's already too late. If they've screwed up, there was no first point at which they screwed up. They always had screwed up. Okay. So that's a reason to think that just because they can do it and want to do it, it's not obvious they will do it. Now, here's an argument that shows that, that's supposed to show that the method that the hat paradox uses actually is so powerful that it leads to contradictions. Okay? And of course, if it leads to contradictions, then it would seem like even though the gods could follow the method in principle, they won't, because contradictions aren't true. So here's how it goes, and this is a little bit tricky. There's two teams of gods. There's the A team and the B team. I call them the owls and the bevs. Okay. And they have different goals. They're both calling off in reverse order. The owl team wants to have their guesses match the bev team's guesses. Okay. So the owl wants all but finitely many of their calls to be the same as the bev team's calls. Problem is, the bev team calls after the owl team. So how it ends is the owl team makes its second last call. The bev team makes its second last call. The owl team makes its last call. The bev team makes its last call. It would seem like since the bev team is calling after the owl team, they have a completely unbeatable strategy for defeating the intentions of the owl team. So the bev team doesn't want their guesses to be correctly ascertained by the owl team. They want to have all but finitely many different calls. The owl team wants them to be all but finitely often in agreement. The bev team all but finitely often in disagreement. Now, the bev team strategy is just like simplicity itself. What is the bev team's strategy to arrange for disagreement between the owl team's calls and theirs? Yeah.
Whatever the owl team calls, don't call that?
Yeah. Now that seems like really like bone dumb. Like, no, you don't have to be a god. A machine could do that, right? Just call, it just computes 1 minus x, where x is, the previous call. So, no problem. So it seems like the bevs have got to win. Someone is predicting what they're going to do, and they just defeat the prediction every time. But the owl team has a strategy too, and it's just the same as from the hat puzzle. The owl team has met beforehand and picked a representative from every equivalence class of infinite sequences of zeros and ones. When it's their turn, they look ahead, so it's owl number n, looks ahead at all of the bev's team's earlier calls, figures out what equivalence class those earlier calls were in, and guesses in accord with that equivalence class. We already have an argument that if they follow that strategy, they'll guess the bev team's calls correctly all but finitely often. So you've got two teams. They want opposite outcomes, and both have a winning strategy. Something's gone wrong there. Teams that want opposite outcomes can't both have winning strategies because they could each follow their winning strategies, and they could arrange for the opposite outcomes, and you can't have opposite outcomes obtaining at the same time. So something, it seems, must have gone wrong. The principle, I guess I haven't been calling out these principles, but the principle here that seems to be refuted by this last paradox is individual power for the gods to each follow a rule, plus the possibility of their all following it together, implies collective power to follow it together. And that just sort of seems like it's got to be wrong, because if that was right, then both teams could execute their winning strategy. It would be within their power to execute their winning strategies. Okay. So now I don't know what to think. I truly don't. But I'm going to give one last example that brings out some of the weirdness of it. And it's a little bit like one I've already mentioned, but I think it's sort of a bit trickier. So we got the owls and we got the bevs. And owls love ones, bev loves zeros. The owls say to themselves, we're just going to call 1, 1, 1, 1, 1 the whole time. The bevs say, we're just going to call 0, 0, 0 the whole time. Unfortunately, government regulations require you to have a fallback plan if what you were trying to do didn't work out. So the owls have to have a plan. They say, look, what if, in fact, it hasn't been a string of ones before it got to me? And they need a contingency plan, and the plan is, if there's been infinitely many departures from the rule, there shouldn't be any, but if there's been infinitely many, then an owl will call 0. So the owls call 1 unless they're infinitely far from reaching their goal. Okay? The bevs want to all call zeros. But they too need a contingency plan. They have a plan that's almost like the owls, but it's even in some ways more radical. They expect to never depart from 0, 0, 0, 0. But they make this rule that says, if we've almost always done what we swore not to, and we've almost always departed from our plan of saying 0 and almost always said 1, I mean all but finitely often, then we'll say 1. Okay? So the owl's plan is say 0 unless infinitely many 1s, in which case say 1. The Bev's plan is say 1 unless all but finitely many 0s, in which case say 0. Now, if I said that right, so how I've described it, it just sort of seems like obvious. The owls are going to call 1, and the Bevs are going to call 0. The contingency plans only come into effect if they fail to do what they obviously can do. Just say a certain number again and again. But now here's the tricky thing. When I explained the owl's plan and the Bev's plan, I sort of made a lot of noise about what they really thought they were going to be doing. And I said, oh, and then there's this contingency plan they're never going to use. And it was a different, that kind of got reversed from the one to the other. So the owls are really going to just sort of keep on saying 1, this is the other thing they do if that doesn't happen. Bevs are just going to keep on saying 0, this is the other thing they do if that's not going to happen. But a change in the tones of voice in which you say, well, this is what I'm really going to do, versus this is my backup plan, cannot affect what rule you're following. It only affects how surprised you are to find yourself following that part of the rule as opposed to another part of the rule. So if I set it up right, the rules, there it is on the handout almost at the end, 1 after almost all 1s, 0 after infinitely many 0s, 0 after infinitely many 0s, 1 after almost all 1s. The first is what the A team is following, the L team. The second is what the Bev's team is following. Those are the very same rule. The only difference is that each team was confident that it wouldn't use the other side of the rule, so to speak. But they're the very same rule. So here's the scenario. If you concede to these teams of infinitely many people the power to follow a rule that they all can easily follow, then you've got to say that the owls come out with all 1s and the Bevs come out with all 0s. But here's a natural thought. If an infinite group of people have the power to bring about a certain result, that power has to be sort of funneled through a certain particular pipe, which is what each of the individuals are doing. The group has a power only via the rules that they get their members to follow. Okay? So he's saying the owls have the power to produce all 1s. The Bevs have the power to produce all 0s. They both have got their members to follow the very same rule, although they didn't really realize that's what they were doing. So however this power is being exercised by the group, it's not via the rules that individuals are following, because it's the same rule in both cases, since that sort of screens off any influence via the individual rules over the outcome. So we seem to have here a kind of a collective agency version of acting at a distance. So this is one group. They together can arrange a certain outcome. This other group together can arrange another outcome. But if you go to the individual members of each group and say, what did you do to arrange that outcome? They say exactly the same thing. They're both following exactly the same rule. So this is a final mystery I leave you with. It would seem that, this is the very last thing, that collective power to achieve a result is exercised via individual power to follow the rule that aims at that result. But this is a counterexample to that, because they achieve different results by following the same rule. Now, of course, my mistake might be that I am crediting both groups with the power to carry out to achieve the outcome, all 1s or all 0s. Okay? Maybe they don't have the power to achieve the outcome, all 1s or all 0s. But if they don't even have the power to achieve the outcome, all 1s or all 0s, if that's not guaranteed in advance, then how do we know in the hat paradox that all those people are guaranteed to achieve the outcome that they wanted, namely guessing in accord with the chosen representative? I don't know the answer to that. It seems like there's got to be an answer. The cases do seem different, but I confess I am confused. So, any thoughts about any of that? Let me see what I can ask you. So here's a question. This is the copycat paradox. So team 1 wants all ones, team 0 wants all zeros. The rule they follow is just say what the previous guy said. Okay. Same rule in both cases. Are you going to get different outcomes or not? That's my question. These guys want all ones, these guys want all zeros. It's totally clear to all of them. They figure by the time it gets to me, it's going to be all ones or it's going to be all zeros. So all I got to do is say what the previous guy said. So my question to you is, it's a prediction. It's an empirical question. We could do it in the lab by getting infinitely many gods in 2 rows. Okay. What actually happens if you get these 2 groups with these different desired outcomes that are trying to achieve the outcome by just saying what the previous god said? What's going to happen? Simpler question. If an infinite bunch of gods want to all say 1, is that within their power? If we all in this room wanted to say 1, I'll bet we could do it, right? Now, I didn't actually check. I didn't count to make sure there are only finitely many people in the room. Now that I look around, I see there are only finitely many people. But even if there had been infinitely many people in the room, I take it that we all could have agreed to say 1 and said, boom, 1, okay? There's no problem with that. Infinitely many agents have the power to all say 1 or 0. Okay? So the question is, when you have the 1 loving team and the 0 loving team, are they actually going to do what they want to do? That's my question to you. Are they going to do what they want to do? Yeah.
I mean, if we're going off what we said about infinitely many people in this room, it's plausible that would happen. I mean, you'd have to get into probability, but there is the ability for everyone to do it, yes. But that doesn't mean it will happen.
So it's not guaranteed. But would you want to say something like this? Well, there's a 0.0001 chance of any individual that they won't do it.
Well, if you're applying that probability, then if that is an initial constraint that the probability is that amount, then yes, it's still plausible, and it's not guaranteed. Yeah.
Well, I was going to say, if there really is that probability for each individual that they won't do it, then it would be overwhelmingly probable that the whole group doesn't succeed, because infinity times 0.00000, big number. So I guess I'd have to sort of go along with you that it's not guaranteed if there's sort of a maximum certainty we could have for each individual. But that's just because what Bertrand Russell used to call it's like there's a medical difficulty there, that we don't always remember what we plan to do, or sometimes our hand gets stuck, right? The gods aren't supposed to have those kinds of problems. So I looked around the room. No, you're all immortals. You're not gods. But even if you'd all been gods, right, reasoning would have been pretty much the same. You're not going to make any mistakes. If you all decide you're going to say 1, you will. Somebody, was it you? Yeah.
So I was slightly pondering the idea of if you've got this set of rules that sort of maybe thinking of it in that you can't have someone who decided the outcome, in that anyone who would have decided the outcome should have looked forward. And so sort of like there's no way to start a sequence. So rather like it's impossible to have this situation where someone's choosing instead.
That sounds like a really good point. So here's what I hear you saying, that I actually didn't give a consistent description of the situation. I said this team wanted to call all 1s. They knew they could do it. They therefore thought it wouldn't make any difference if they just copied the previous people that were calling 1. But we forgot that every single one of them is going to be just copying the previous person. So now it's very hard to see how they're supposed to implement their desire to call 1s. What's really true is that if the sequence starts out right, then past a certain point, everyone could just call what the previous person did. But for them all to do it, maybe that's where the problem arises, and that seems right. And that could be part of what's wrong with the last paradox I mentioned too. But what about that, what I called the copy hat paradox? It's got the word bacon after it because it was invented by a guy named Andrew Bacon. That really does, if there's one paradox on this list that's really challenging, that's the one. It really does seem to lead to a contradiction. What is going on? Yeah.
I'm puzzled too. I don't know what to do with it. But here's something that seems relevant to me. So in setting up the problem, you divided the group into the Ls and the Bevs. But that was just an artifact of that particular description. One could think of them all as a single group, and you could think, well, okay, so here's our pre-game plan. Just like the even-numbered people do one thing, the odd-numbered people do something else. And when we think of it that way, the collective plan is impossible. So then, as long as you have a rule that says, whenever collective plans are impossible, the group isn't going to do them. You can block that, and that rule won't block the regular hat paradox.
Yes.
I mean, I'm still puzzled, but I don't know. That's the difference.
So let me give an analogy, a very simple-minded analogy to what you just said, and tell me if this is right. So here's something that I can always do. Pick a bigger number than you picked. Here's something that you can always do. Pick a bigger number than I picked. Well, you could imagine a team with you and I, and our joint goal is to each pick a bigger number than the other one picked. That's not going to work, right? And so then the question is, what went wrong? And maybe we have to just, here there's sort of temporal issues that are kind of distracting, but maybe what's going on in the case of the copy hat paradox is, look, it is impossible for them both to do what they're supposed to do. Thinking of them as one group, they can't carry out their plan. But if they can't carry out their plan, it's because one of the subgroups can't or the other one can't. Maybe the mistake is to think that there's a definite one, that it's got to be them, right?
I like it. I like it.
Yeah. But I still think it's weird. Yeah, anyway, yeah.
Steve, this was brilliant. Thank you so much.
Thank you guys. You're great.